All right, so today I'm going to we were rushing through the end yesterday, so I want to revisit that, and then we're going to do some example problems. Let me just read you what's on the agenda for today. Today is 22nd, Friday. So you're going to watch and take notes as I wrap up yesterday's discussion, and then we're going to work some example problems. There is a new quest assignment. It will be due next Tuesday. We will work on it in class on Monday. We will not meet on Tuesday, though, so you're going to be on your own on Tuesday because you're also going to be doing the PSAT. Good. All right, and then...
Do you have information for seniors about that one?
No. I have information about the SAT for seniors, if you want to know. I'm sure that you come late or something. Ask me on Monday. I'm sure I'll get an email on Monday. So what you picked up on the way in, it's the first 2 pages of our 3-page simple harmonic motion MCQ test review. So we'll be working on that next week as well. But I'm going to take a few problems from it to reiterate some concepts from yesterday and today. As you'll see, some of the questions that we can see for simple harmonic motion for mass spring oscillators can be a little confusing. They can be a little tricky, and you got to be a little more cognizant and a little more aware of what's going on in order to answer them. So so we're going to do those examples today so that you can get a good head start on the quest assignment. All right, that being the case, we're going to look at the rest of the example problem from yesterday. We did calculate D, but we went through it real quick. Part E, I'm going to do first. Part E, I'm going to talk about first. And so this is what we talked about at the end there. The amplitude of the oscillation, we have a mass on the end of a spring. It is oscillating. And honestly, I'm going to say this is the only class that I feel like it's an issue with. There's no need to have computers open right now. So if you have a computer open, please close it. There's no need to have it open. You're listening to me. You're watching me. So please don't have your computers. Don't look at your phones. So we're going to change the amplitude of the oscillation, and we're going to see if the period is affected. Normally, we actually do this experimentally, and I could do it up here, but let me actually do it with this mass spring oscillator. So you can see that it actually works in real life. So I have this mass spring oscillator, and I want to measure the amplitude, or measure the period. Okay, so I'm going to use my timer on my phone. I'm going to stretch it a little bit and just let it go and then measure this period. Now, do you think if I hit start and then stop after one oscillation, do you think I got a good measurement for that period? No, there's going to be a lot of error there, right? I did it. And so what's a way that I can actually reduce my error in that measurement?
If you lap it and then
Yeah.
continue to count down.
I just do multiple oscillations and then divide the total time by the number of oscillations. So I'm going to pull it down and I'm going to hit start. 1, 2, 3, 4, 5. So I did 5, and I get 5.12 seconds. So I'll say up here, I'll write this up on the board. Obviously, there's some error here too. If I was doing a real lab and I wanted real results, I would do at least 10, even more. So I have 1.02. So our first period is 1.02 seconds. Now I'm going to do it again, but I'm going to have a larger amplitude. I guess I could have lights on for this. I'm going to have a larger amplitude. So I'm going to pull it down significantly farther. So now I have a much larger amplitude, right? And I'm going to do the same thing. I'm going to hit start. 1, 2, 3, 4, 5. And I get 5.21. What's 5.21 divided by 5?
1.042.
1.04 seconds. Within the realm of experimental uncertainty, due to the crudeness of the experimental setup, those are the same values, right? And I significantly changed. I went from like this amplitude to this amplitude, and we saw it was the same period, okay? So the answer to that question is that it does not change. How can I justify that, though? I can justify that answer. By the way, you can ignore all this. I needed this up for my physics C class next period, and I don't have time between this class and that class to do it. So all of the work today will be over here. So actually, let me zoom in on it over here. So how can I justify that answer? Well, I have an equation for the period of a mass spring oscillator. It is the period of a spring is equal to 2 pi times the square root of the mass attached to the spring divided by the spring constant of the spring. Do I see an A in that equation? No. Therefore, the amplitude does not affect the period. You can justify it that way. There's no amplitude in the equation for the period of a mass spring oscillator. That's fine. So the answer there is it does not change, or it remains the same, because the amplitude does not affect the period of a mass spring oscillator.
Could you also say that in the period of a mass spring oscillator, the mass and the constant are equal no matter what the amplitude is? So
Are what?
the mass and the constant are equal no matter what the amplitude
Yes.
is? So,
Yeah, that'd be fine. That'd be just yeah. I'm stumbling over my words today. All right. Now let's look at number D real quick. We did this yesterday, but we were kind of rushed. It said what's the frequency of the oscillation, and to figure out the frequency, well, there's actually two equations, but the most easy way to figure out the frequency given most problems is using this equation. The period is 2 pi divided by the angular frequency, which is equal to 1 divided by the frequency. So if you know the angular frequency, you can get the frequency and the period. If you know the period, you can get either of the frequencies. Right? If you know one, you can get the other two. And so what I can do is figure out the period and then use that to determine the frequency. So the period of a mass spring oscillator, and sorry, let me write like this. Hopefully we can say that if we know the period is inversely proportional to the frequency like this, then I can rewrite this equation as the frequency being inversely proportional to the period. Right? Those are equivalent. If you need to multiply both sides by f and then divide both sides by t, you get that result. Okay. Yesterday I went through this kind of quickly. I said, well, if I'm dividing 1 by the equation for the period of a mass spring oscillator, it's 2 pi square root of m over k. Those of you with really good algebra skill, you can actually do this in one step and say this is 1 over 2 pi times the square root of k over m. Last period, I had a student or two, they're like, and so let's go through how you would actually do that. You got to know your properties of radicals. At this point, you all should know your properties of radicals. That's algebra 2, right? Properties of radicals?
I can look at algebra 1.
Algebra 1, maybe, yeah. So let's actually look at this. If I want to know the frequency, it's 1 over 2 pi times the square root of m over k. I'm going to rewrite some stuff, a few steps. Rewriting is key. In calculus, you know that to do a lot of problems, it makes it a lot easier to rewrite it in a more convenient form. So you can see some stuff. So I can rewrite this as 1 over 2 pi is in the numerator. This is a compound fraction, so I got to deal with the compound fraction.
2 pi is in the denominator.
In the denominator, the 2 pi is in the numerator. Sorry, I should have said that. If I'm looking at just the denominator, right, 2 pi is in the denominator, yes. But if I look at, when we have a compound fraction, we have to divide the numerator by the denominator because one or both are going to be fractions. So in the denominator, 2 pi is in the numerator. So I can write it as 2 pi over 1. And then using my properties of radicals, I can say, well, the square root of m over k is the same thing as the square root of m divided by the square root of k. Just like the square root of x times y is the square root of x times the square root of y. Now and then I can make the numerator fraction by just putting it over 1. Now I have a more easy compound fraction. The denominator here, I can just write like this. The squeak. Can we stop the squeak? You can shake your legs. I bounce my legs all the time, but if it's making a squeak, then just move to a better location. So now I just flip the guy and multiply the top by the reciprocal of the bottom. So it'll be 1 over 1 times the reciprocal, which is the square root of k, over 2 pi times the square root of m. Well, and then just like I can take square root of k over m and turn it into the square root of m divided by the square root of k, I can take the square root of k divided by the square root of m and write it as the square root of k divided by m. So I'll have 1 over 2 pi, right, because he's still in the denominator, times the square root of k over m. Some students commit that to memory, but if you're at this level and you're like on your way to calculus, you're already in calculus, you really want to be able to do like this to that relatively quickly. I won't say in your head, but if you can, then you're in good shape. If you can't, that's okay. but just know that you have to use your properties of dealing with compound fractions and then dealing with radicals in that way. Sure. All right. And so now I have an equation for the frequency, though. The frequency is 1 over 2 pi times the square root of k over m, which we can all do in our heads, I'm sure. 1 divided by 2 pi times the square root of the spring constant, which we determined already is 500, divided by the mass, which was 2, I believe. And that comes out to be 2.5? 2?
I said if you keep it just multiplying, it's 15 over 2 pi, I think. And then 15 divided, I don't know what 2 times
Is it?
pi is.
It is 10.06.
The square root of 250 is not 15.
Well, you have 500 over 2, you divide that, that's 250. Square root of 250 is 15, I think.
225.
Yeah, it's 225. Square root of 225 is 15. Divided by 2, square root, divided by 2, divided by pi. I got 2.52. And it is a frequency, so it's 2.52 hertz. There's our frequency. Double check me on that, but I just did it twice, and that's what I got.
Yeah, it would make sense.
Okay. Cool beans? Alright, so that's the example problem. We've done all parts now. That is a nice example FRQ for this. Now I'm going to erase everything, if that's alright. I guess I should have waited before I started. Alright. Now we're going to go to the worksheet that you picked up on the way in, and we're going to do numbers 4 through 8 and numbers 11 through 13. And as you'll see, some of these questions are not as straightforward as you might think. And so let's look at number 4 through 8. 4 through 7 are going to be together. Number 8 will be a separate one. 4 through 7 says the equation which describes the motion of a mass oscillating on an ideal spring is x, standing for position, equals 6 times the cosine of 3t. And I like using parentheses there just to ensure that the argument of the trigonometric function is right there. All right. The first question says, number 4 says, which of the following statements is true for the oscillator at time t equals 0? At first glance, this seems very difficult looking at it. The acceleration is 0, the velocity is 0, the net force is 0, the potential is 0. How would I do that? Well, note that this looks eerily similar to what I showed you yesterday. Without numbers, with just symbols, this kind of looks like a cosine angular velocity times time. Again, that's not what's on your formula sheet. What's on your formula sheet is x equals a cosine 2 pi frequency times time. This is one of the things that annoys me about the College Board's AP Physics 1 formula sheet. This is what's on the formula sheet. This is more useful. This is actually a lot more in line with what we do in AP Physics C next year when we do our simple harmonic motion unit, which involves differential equations and calculus, which is cool. But we use that angular frequency a lot more in higher levels of physics and engineering than we use normal frequency. It's much more useful. It makes the math actually a lot easier, even though the concept is a lot more difficult to understand. This is what's on the formula sheet, though. And so if you forgot how I got from here to there, well, I use this equation. And just look at this part of it. If you solve this for frequency, you get omega over 2 pi. If you plug that in for frequency here, the 2 pi's cancel out, leaving you with omega times t. Which tells me that, well, let me ask you guys this. Do we know given this equation here, do we know the amplitude of that simple harmonic oscillation? It's 6. There's a problem here, by the way. It says 6 centimeters, or it says x is in centimeters in the setup, but then in numbers 5 and 7, it actually says meters. So that's a mistake that Alex made, so blame her. So the amplitude here is 6 centimeters. What else do we know from that?
The angular.
The angular frequency. Angular frequency is 3 radians per second. This is that weird radians per second. Yes, it is an object moving in a straight line back and forth, but we can equate it with circular motion of an object moving back and forth with an angular frequency. Okay. So that's what we know. So when the question asks us, actually we're not even there yet. Wait. Which of the following? Sorry, this is the setup. This is the information we can get from the equation. Number 4 says, which of the following statements is true for the oscillator at time t equals 0? And so at time t equals 0, and we can actually get this from either one of these equations, at time t equals 0, x, and you might think of it this way, x is a function of time, right? Time is the variable here. The frequency and the angular frequency are going to be the same. 2 pi is always the same. So the variable is time. So x is actually a function of time. And so what happens to this equation? What's in the argument of the cosine when the time is 0, regardless of which version we use? 0. And the cosine of 0 is uno. Right? So x is at the amplitude. So what this is saying, it's not explicitly told to us, but what we can glean from this is that at time t equals 0, the object is at the maximum positive amplitude. Okay? So if I was to draw a picture, got a mass attached to a spring. We know that at this point, it's at the maximum positive amplitude. If this is equilibrium, then this would be negative amplitude. We know that the spring is at that location in its oscillation at this time. Can x be any larger than the amplitude ever? No. Why?
Because the amplitude is not just the distance, and x can't go over the distance.
Right, but mathematically why? I mean, we know based on what we already know that the mass is never going to go beyond the amplitude. Well, a term outside of here would actually just shift the graph up or down. Yeah.
You'd have to change the amplitude in order for the position to change.
You'd have to change the amplitude in order to get a different maximum position, right? What I'm getting at here is that the cosine of the angle, and I know we get kind of lost here because we haven't talked about it in terms of SOHCAHTOA in a while, but the cosine of the angle, we're dealing with right triangle trigonometry. This is the adjacent side, this is the hypotenuse. Cosine of the angle is the adjacent divided by the hypotenuse. What's the maximum magnitude that the cosine of any angle can have? What's the maximum value that the cosine of any angle can have? 1. It cannot be any bigger than 1. Because if cosine of an angle was bigger than 1, that would imply that the adjacent side of a right triangle would be longer than the hypotenuse. And that's literally impossible, right? If the adjacent side here was longer than the hypotenuse, then it wouldn't be a right triangle. So the cosine of the angle, which is the adjacent over the hypotenuse, is less than or equal to 1. Now, specifically the absolute value, right? The magnitude of that value, because it could be negative 1. It could be negative 1. The cosine of pi radians is negative 1. The cosine of 0 radians is 1. If you're in Algebra 2 and you don't know that, that's fine. Your calculator knows it. But just understand that that's why mathematically the maximum displacement that we can have is the amplitude. We already know that just intuitively and by what we've talked about before, but just understand that mathematically is why. And it kind of brings back what cosines and sines actually tell you. They tell you about the ratios of side lengths of right triangles. And those in pre-cal, that forms the basis for your unit circle, right? Every point on the unit circle that you got to memorize what the cosine and sine is, you just draw a little triangle there. It's either a 45-45-90 triangle or a 30-60-90 triangle or just a straight line up, right, left, or down. Okay, that was a little aside. But we know at time t equals 0, then we're at maximum amplitude. And maximum amplitude, our position vector is positive. So what must be our what direction must our force vector point? The spring force. It must point to the left. And that spring force, remember, it changes as the object moves, but once it gets to the maximum displacement, it is a maximum spring force, which by Newton's second law tells us we also have maximum acceleration. Not maximum velocity. What's our velocity there?
Sorry, zero.
Velocity 0.
I thought you were saying whenever it moves and it goes to equilibrium.
At equilibrium, we'll have maximum velocity and 0 force and 0 acceleration. So anyway, so which of the following statements is true for the oscillator at time t equals 0? C, the velocity of the mass is 0. Let's look through them all, though. The acceleration of the mass is 0? No, the acceleration is at a maximum. B, the net force on the mass is 0? No, the net force is at a maximum. The elastic potential energy of the mass is 0? No, the elastic potential energy is at a maximum. Notice how we got here, though. We had to determine this. We had to take this equation, put in 0, figure out that the position at time 0 is at the amplitude, and if, maybe you're talking about putting plus or minus something in the inside of the bubble. Is that what you were talking about before? We're not going to deal with that in this class. You'll deal with that in your pre-calc class. I'm assuming that's what you meant.
Even calculus.
Oh, really? Oh, you're in calculus? Oh, I knew that. Are you a senior? Oh, wow, you're one of those smart kids. Not that all you other guys aren't smart kids. So yeah. Now I'm lost. Why'd you distract me like that, man? Jeez.
Equilibrium of the spring. It's going to have 0.
We got it, right? We got it. The point was that you had to know at time t equals 0, the position is the amplitude, and then you either have to mentally or draw a little picture to realize, well, when you're at the amplitude, positive amplitude, you got maximum negative force, maximum negative acceleration, 0 velocity, right? Maximum potential energy. Doesn't matter if x is positive or negative, potential energy is always positive. Always positive because it gets squared. Okay, number 5, the amplitude of the harmonic motion is, we already said that. It's what? 6. Technically it's centimeters based on the setup to the problem, but the answer choices do say meters. Again, I think I blamed Alex for that one. Thanks a lot, Alex. The period for the period of vibration for this mass on the spring is most nearly. Well, how do I get the period from what I'm given?
Is it 2 pi plus 30?
We can't use that one. That's a good question, but we don't know the mass. We don't know the spring constant. What? Well, we don't know the frequency either. There we go. We know that the period, this is part B, we know that the period is 2 pi over the angular frequency. We know the angular frequency. The angular frequency, just by looking here, is 3. Right. Again, that hinges on you can match this equation with this equation, which is not on your formula sheet, but which you can derive by combining this equation with that equation. It's annoying. This one I would write on my formula sheet just to get it in my brain. This one, especially for future STEM majors, because that's the form that you're going to use way more often in higher levels of physics. So it's going to be 2 pi over 3. 2.095, 2.1. 2.1 seconds. Period is in seconds. 2.1 seconds. And so that's most nearly, it does say most nearly. The period is most nearly 2 seconds. This next one, I said B, that's number 5. Number 6. That's number 6. Number 7. A lot of students get this wrong. What's the total distance traveled by the mass? I'm sorry. Total distance traveled by the mass during one full oscillation. That's the... It'd be double that. If you go from the amplitude, you cover one amplitude to get to equilibrium, one more amplitude to get to the negative amplitude, but that's only half an oscillation. So then you have, on the way back, you cover the same distance. So that's a very common question, so get that in your brain so you don't make that mistake. It's an easy question if you just think about it for a second. You cover the amplitude 4 times in one complete oscillation. Just like in one complete cycle of a sine or cosine graph for those in pre-cal, you cover the amplitude of the graph 4 times in one period. So it's 24. Should be centimeters, but it says meters. Sorry about that. All right, number 8 is a different problem. Number 8 is a different problem. There's a couple ways of answering this. We have a position, vertical position versus time. So it's like an oscillator, like what I showed you at the beginning, where I have a mass on the end of a spring that's oscillating up and down. And it says a particle oscillates up and down in simple harmonic motion. Its height, y, is a function of time t, shown in the diagram above. Which of the following is true for the velocity v and acceleration a of the object at t equals 3 seconds? So 1, 2, 3, 4 seconds. Those of you in pre-cal, what kind of a graph is this? Cosine. That's not cosine.
It's negative sign.
Negative sign. Yeah, there you go.
Sorry, I did. Yeah.
I probably could have phrased that question better.
No.
Do you need to know that to answer the question? No. No, you don't. You need to know, you either need to be able to connect that graph, the position graph there, with the motion of an oscillating mass, like in your head, or look at it because it's oscillating up and down right now. Or you need to know how to deal with motion graphs. This is position versus time graph. What's the slope of a position versus time graph tell you? Velocity. You guys need to know that. That's second nature to this level. You're at this level of physics, you must know the information that you can get from a motion graph. That's considered to be prior knowledge at this point. So the slope of this graph, obviously the slope changes, but the slope at this point is what? 0. The slope of that tangent line there is a horizontal line. That's slope 0. So if the slope is 0, the velocity is 0. So we know the velocity is 0. But then we need to know what the relationship between acceleration is 0 and 0 is. It's either greater than, equal to, or less than. Now you can't use, to get acceleration from position time graph, we don't really do in AP Physics 1. We do in AP Physics C. You do in calculus, but you don't do in AP Physics 1. But we can say, all right, well, at this point, the object is at maximum amplitude, 10 centimeters. At this point, at 1 second, it would be at the minimum amplitude, negative 10 centimeters. So when this guy's bobbing up and down, when he's at the maximum amplitude, what direction is the acceleration? Down. So is that positive or negative? Negative. So is the acceleration greater than or less than 0? Less than. All right. So this stuff, I just want to emphasize, it can be tricky. This stuff can be tricky. It's not as straightforward as a lot of other stuff that we do. Not that a lot of stuff we do is straightforward, but some of it is. This is not. You got to make some connections in your brain. You got to rewire the neurons or whatever happens whenever you get smarter. Oh no, that's biology. Yeah. You ever learn so hard that your brain starts hurting? You're creating new neural pathways. You're literally getting smarter. That's why people that fight learning, that's why they don't get smarter, because they don't actually exercise their brain enough. I don't know if that's true. I don't know biology. But that's beyond the scope of this class anyway. All right, so that's the answer to number 8. Any questions before we move on to 11 through 13? Are we good, Gavin?
Hey, you just want to do 13 or you want to do 11 through 16?
11 through 13. Sorry. Did I say? Yeah, 11 through 13, if I didn't say that. Okay. And I'm just going to, just to make sure we have enough time, I'm going to note everything as I come across it in the problem. When a 0.2 kilogram block, so my mass, 0.2 kilograms, is suspended from a vertically hanging spring, the block stretches the spring from its original length of 0.05 meters. So originally, the spring is at 0.05 meters. So that would be this distance here, 0.05 meters. It stretches it from the original length of that to 0.06 meters. And so that's with the mass attached to it. So this would then be 0.06 meters. Drawing not to scale. The same block is attached to the same spring and placed on a horizontal frictionless surface. Notice this is very much like the example problem that we've already done. So I take that same block and attach it to the same spring on a horizontal surface. And if the spring's relaxed length here is 0.05 meters, that will be the same length here, 0.05 meters. And this will be the equilibrium point. That's where the spring is unstretched, uncompressed. Okay. The block is then pulled so that the spring stretches to a total length meaning total from this point to wherever we stretch it to, total length of 0.1 meters. So I essentially double the distance. And so I've stretched it to a total length of 0.1 meter. The block is released at time t equals 0 and undergoes simple harmonic motion. What is the frequency? So number 11 says, what is the frequency? Now, if we had a little more time, and we might have had it, I just wanted to be sure. If we had a little more time, I would have started by just saying, what's the frequency, based on everything I just read. And very often, and this is kind of, I'm not going to say we haven't seen this before, but this is where it's like really rears its ugly head. Very often, it's like, you get all this information about a situation, and then you get asked for something that seemingly is not related directly to what we've just been talking about, or what you've just been given. Here we get information about spring stretches, masses, and then we're asked for a frequency. Well, the equation that I know that involves frequency is this one. T equals 2 pi over omega, which equals 1 over f. That, and then the position function, right? We do have this one as well. X equals a amplitude cosine 2 pi times the frequency times the time. That is another equation. But I can guarantee you in AP Physics 1, you're never going to solve for a variable that's inside the argument of a sine or cosine. Sine or cosine. But in pre-cal, you've obviously done that, right? You can solve for f here if you needed to. If you knew x, a, and t, which we don't know. We do know the amplitude. We don't have a position per se. We do know the position at the amplitude, but then we don't know we don't know the time, so we can't really use that. So yes, that is an equation that involves frequency, but we can't use it. So we're going to have to get the frequency from this equation here, but we don't have the angular frequency, and we also don't have the period. So what can we do? Can we find the angular frequency?
Is there not an equation for angular frequency?
The only other equation that has angular frequency is the one that's similar to the one for regular frequency, and that's this. But again, we don't know what time we're dealing with. We don't know what position at that time is. So we can't really use that one either. We would need more information. We would need more information about the position as a function of time in order to actually use that function. So it boils down to this. We got to use this. Yes, sir?
You could do f equals 1 over t.
So f equals 1 over t. Do we know the period?
No, but you can turn the period into 2 pi square root of m over k.
Okay. So I can say, now we already did this in the example problem, so I'm just going to write it. 1 over 2 pi times the square root of k over m. Let me box this guy. We do know m. Do we know k?
Well, you can find out vertical situation.
Just like we did in the example problem. This is very common. And this is actually the easiest, not the most accurate, because you want a lot of data points to do any scientific experiment accurately. But if I want to know the spring constant of the spring real quick, I measure the unstretched length, and then I hang a mass on it, let it come to equilibrium, measure the new stretch length, and analyze the forces here with Newton's laws, and then use that to determine the spring constant. So when it's at this point, and we did this with the first example, when it's here, we have an upward spring force and a downward weight force. And if it's at equilibrium, it's equal. And we're told that when you hang the mass on this guy, it moves down to 0.06 meters, and we assume that's the new equilibrium position. And we know that the spring force is, the magnitude of the spring force is K times the magnitude of the displacement. Our free body diagram tells us it's positive, it's pointing up. Right? And we know that Kx must equal mg. Kx must equal mg because the mass is at rest here. And so we can divide both sides by x and get that the spring constant is simply mg divided by the displacement x. This worksheet does say use 10 for g, and so I'll have the mass of 0.2 times 10 meters per second squared for g, divided by the displacement of 0.01 meters for x displacement. And 0.2 times 10 is 2. 2 divided by 0.01 is 200. So it's 200 newtons per meter. Now that we have the spring constant and we do have the mass, now we can find the frequency. So I take that equation, 1 over 2 pi times the square root of k over m. It's going to be 1 over 2 pi times the square root of 200 divided by the mass, which is 0.2. You should all be able to do this in your head. Gavin, what's the answer? Oh my gosh, you can't do that in your head? I can, but I just want to be careful.
Wait, so Mr. I'm confused. What equation is the Kx equals mg from?
That's by using Newton's first law.
Okay.
The object is at rest, so the forces must be balanced. So I draw a little free body diagram, and then I know that the spring force must equal the weight force, and then I can just set those guys equal to each other. You could say net force equals mass times acceleration. The acceleration is 0, so the net force is 0. So Kx minus mg equals 0. Add mg to both sides, Kx equals mg. And when you work through all that, I get a frequency of 5.03. 5.03 hertz. All right. Number 12, complete the following statement. In order to increase the frequency of the motion, one would have to, well, let's look at this equation that describes the frequency. The frequency, as we derive, and this is another reason that you want to generate the equation before you plug in numbers. Because then when you get a question like this, you can just look. If I want to increase the frequency is directly proportional to the square root of k, both in the numerator. One goes up, the other goes up. One goes down, the other goes down. Directly proportional to the square root of k. So if I want to get an increased frequency, I can increase the spring constant. None of the answer choices for number 12 say increase the spring constant. What else could I do in this equation? In the interest of time, I just got to say it. The frequency is inversely proportional to the square root of m. Square root of m is in the denominator. Frequency is in the numerator. If one goes up, the other goes down. Or if one goes down, the other goes up. So if I reduce the mass, then I get a larger frequency. Okay? Meaning it goes back and forth faster, smaller period. So that is B. You decrease the mass. If you reduce the spring constant, you'll actually reduce the frequency. Stiffer springs, higher spring constant, they vibrate faster. Right? Real loose springs are very sluggish in their motion, like that one. And then reducing the distance or increasing the distance changes the amplitude, which, as we already saw, doesn't change the period or the frequency. And then 13, which one of the following statements is true concerning the motion of the block? The magnitude of the acceleration is constant. Simple harmonic motion, that is never true. That's why we can't use the kinematic equations. The magnitude of the acceleration is greatest when the spring returns to the 5 centimeter position. At 5 centimeters, the spring is not extended or compressed. So this force is 0. So Newton's second law tells us the acceleration is 0. So that's not right. The period of its motion depends on its amplitude. We've said that several times at this point. The period is not dependent on the amplitude or the frequency or the angular frequency. None of them dependent on the amplitude. The magnitude of the velocity is greatest when the magnitude of the acceleration is greatest. That is also not true. That's the counterintuitive thing. The maximum velocity happens at the equilibrium position. When there's no stretch or compression of the spring, no spring force, no acceleration. And E, the magnitude of the acceleration is greatest when the mass has reached its maximum displacement. That is true. Maximum displacement Yes, zero velocity, but you get maximum force. Maximum force, Newton's second law tells us that you get maximum acceleration. Okay. So there's some problems dealing with what we talked about the last couple of days. Yeah, that's it. There's a new quest assignment you can get started on. We will work on it on Monday in class. It'll be due Tuesday night, but Monday's the only period that we'll be working on it in class. Okay. And as usual, it will be worth 2 daily grades. Online students, sayonara.